Object-oriented programming. Thus far in our training, we've been using Python mainly in its procedural paradigm, but as you know by now, one of Python's great strengths is that it's multi-paradigmatic. That is, we can do procedural programming, object-oriented programming, which of course is what we're concentrating in this nugget, and even functional programming for those that are into the so-called meta-programming thing. In this nugget, we're going to lay a formal foundation in OOP principles. We flirted around with the subject a little bit in earlier nuggets. We're going to flesh it out, build upon it, and then in the subsequent nugget, when we do graphical user interface design, we're going to be transparently applying everything that we learn in this nugget on creating and using classes. There's a lot to learn in this nugget, so let's get going. So what is object-oriented programming anyway? OOP we're going to contrast with procedural programming, which we've done largely in this nugget series so far. Procedural programming is where you're pretty much structuring the flow of your application from start to finish and then trying to capture any edge cases, any sub-procedures that the user might decide to go down in your user interface. You'll also recall that the way that we modularize or separate out components of our program in the procedural paradigm is by using functions. Now that's all well and good. It componentizes your program to a certain degree. But what about the issue of code reuse? That is to say, what if we've created a function that does some work for us that's all well and good, but then elsewhere in the program we want to use the same basic function, but perhaps add just a little twist on what it does to suit a different need in our application. As you see here, you wind up pretty much just copying and pasting and tweaking your code on your functions, and you wind up at the end of your application with all sorts of functions. I call them Franken functions that are slightly different. They all have the same basic mechanics, but there's no link among any of them. That is, if we were to update this original function that we used as a template, there's not going to be any inheritance by the other instances of that function in our code. You see? So procedural is a really nice programming paradigm. It'll get the job done, but the main reason why folks tend to be OOP nowadays is because instead of just a row of functions, we can then create objects that are freestanding and or relate to each other, and each object has encapsulated within it its own functions. We know by now that functions inside of classes are actually called methods, and other attributes, you see? So you wind up with these self-sufficient containers called objects, and what's nice about these class objects is that we can just spawn as many instances of each object as we want to in our code. As a matter of fact, there's an important aspect to object-oriented programming design. In fact, it's more than an aspect, it's what's called the design pattern. And what design patterns are in object-oriented programming are different schemes for implementing OOP in a development environment to solve your problems. I would specifically recommend you check out the O'Reilly book, Head First Design Patterns. I've read a lot on OOP design patterns, and that book tends to be the most approachable for those who are beginners in this subject. Alright, so what else about OOP that differentiates itself from procedural programming? Well, in OOP we can really boil the syntax of it down to just this guy right here, object.attribute. We've been using this so-called dot notation a lot in the course thus far. Even aspects of Python that aren't ordinarily considered OOP actually are. You might recall that in Python 3, when you run the type function, you wind up with class equals string, let's say. Let's say you've created a name called foo, and then you run the type function and pass in that A, you're going to get class equals str, because under the hood, the actual design patterns of Python itself is OOP now. There's really not much of a way that you can avoid OOP in contemporary programming. So we use this dot syntax, as previously discussed, to access the attributes of an object. Now some of the terminology gets a little bit muddy here in Python. For instance, you might have a class object that you've instantiated that you then can use dot notation to call methods or functions that operate on that object. You also can use dot notation just to define what are called properties or characteristics of that object. All right? More on that in just a little bit. The bottom part of our whiteboard here shows us the relationship among objects in an object-oriented programming paradigm. One thing you're going to have to understand about this inheritance deal is that in objects we have encapsulated within it all of its core functionality. So we start with a class, which, as we've discussed in the previous nugget, is more or less an instance factory or a template for creating other objects. And in that superclass, we have methods and attributes that are encapsulated within this object and are usable immediately by instantiating or creating an instance of that class. What's also especially flexible about OOP is that you can avoid this problem that we saw over here with functions where we have similar functionality required and we just wind up manually modifying copies of a base function. In OOP, we can do what's called a subclass, which is kind of the equivalent of doing a file save as operation in an Office productivity application, where you have all of those methods and attributes that are contained in the superclass copied down through inheritance in our subclass. And remember, a class is not usable directly. A class is used as an instance factory. When we instantiate an instance of a class, that instance becomes an object in its own right, and again with the flow of inheritance. In this case, we have a superclass called A. We've subclassed A as B here in the middle, and then we've invoked an instance of this subclass called C. The law of inheritance says that C now can transparently access all of the methods and properties of both B and A. If you have familiarity with name resolution in TCP/IP networking, you know how the order works, right? A computer will look in its own DNS resolver cache in memory first to look for a name to IP address mapping. Then it'll go to the file system and look up a hosts file and see if there's a mapping in there. And then ultimately, if that client computer is configured to talk to a DNS server, a DNS lookup is performed. Similarly, when we've instantiated an instance of a class and we're actually using this instance in our code, when we call a method, let's say .y, the Python interpreter needs to figure out where that method lives. So what'll happen is you wind up with what's called a tree search. As Python starts with the instance and what it has in its local collection of methods and properties for that matching object. If it's not there, it'll then come up to its parent class, in this case B, and look through its list of methods and properties. If it's not there, we'll go up yet another level in the tree to the superclass on which this subclass was defined and look for methods and properties there as well. Now, one thing that may be coming to your mind is you notice that there's a method called X in the A superclass, and we've also defined a method named